Alright, let's get started. So in the last class, I discussed some of the principles of dewatering and also some principles pertaining to standpipes and piezometers. So we'll try to finish off this dewatering section today and move on to grouting and deep mixing. We've seen this slide already in our lecture. So anytime we're dewatering, we have two choices, either shallow sump pumps or well pumps. And this is, of course, dictated by whether you have the resources to dig a trench or you have a borehole to place a deep well point. Deep wells are most commonly used for deep excavation projects, as you can probably expect, because we need to be able to draw down the groundwater table inside the excavation to formation level. And we usually do this progressively. So for your capstone design projects, you usually, as you excavate in Plaxis, you have a diaphragm wall here. If you carry out stage construction, let's say you excavate this, and then at the same time, the green is the formation level, you have to lower your groundwater table about 1 meter below. And then if you lower your excavation level again, then in Plaxis you need to consider the reduction in your groundwater table about 1 meter below during the stage construction. So this is what we do in routine construction anyways, industry. So these are deep wells, and this slide shows a summary of what type of dewatering technique you should do depending on the type of soil conditions available. If you have something very pervious on the left side, you can basically use any type of well you'd like. In the middle here, in this region, we still have sandy material, so it's very permeable, very pervious. Well points are well used. You can use sump pumps, and you'll get very quick and rapid hydraulic response in the ground. As we increase the content of silt and fines in this next region, you'll find that it becomes more and more difficult to pump water out of the ground. And eventually, if we progress towards the clayey region, you won't be able to pump water out of the ground using pumps very easily. You'll have to rely on special osmotic approaches called electroosmosis, which is the method of forming some sort of gradient in order to let the water drive from a high gradient to low gradient, a high potential to low potential based on the gradient. So these are, in essence, the suitable conditions for dewatering. Last week I mentioned there was a type of reclamation called, I think it's polder. The polder is, in essence, when you have, I forgot to tell you the name last time. If you have a sea here, and then you create a seawall, and instead of, let's say this is your land here, this is the home. Instead of trying to fill all this area with sand behind the seawall, as we would conventionally do, what we do for a polder design is we don't fill it with sand, actually. We create a series of pumping stations inside here. And canals to try to suppress the groundwater table inside. If we can keep it low, inside this area, then we actually don't need to waste money to replace we don't need to fill up this area with sand. And that can save us a lot of money, right? In terms of having to find replacement fill material. So this type of technique is mainly used in the Netherlands. That's where it originally came from. And more recently, it's been used as a trial in Singapore. And it's underway. So this is quite interesting. A polder is what this low-lying region is called. Some areas in the Netherlands use this for farming. Some areas use this for, well, even commercial buildings as well. So this area is very long. We're talking about kilometers. It doesn't look according to scale here. Of course, the limitations of polders, as we mentioned in the last class, you need to continuously pump and control the influx of water. It could be quite dangerous if there's a sudden storm surge, especially for low-lying ground that's below sea level. But otherwise, if you have a polder, you can still make use of the land and also not require fill material. So I forgot to mention last class about polders. So anyhow, moving on, I mentioned about cofferdams. So what you see on the left here is a cofferdam. We have two well points. The well points are taking water out from these 2 points. We have another well point here. We have the initial groundwater table shown with this orange line here. This well point here is also referred to as a recharge point. I'll explain why. So if we just dewater, we can actually suppress this orange line, perhaps down to here. And the problem with the blue line is you can see that there are two footings here, right? We may be causing some sort of consolidation underneath these two footings, which would mean that we could see differential settlement. If this is supporting some sort of bridge or pedestrian bridge above, then that may cause problems. So anytime we carry out dewatering works, you notice that we carry out sensitivity analysis of the surrounding site beforehand. Let's say we do excessively draw down. So let's consider the blue line as an excessive drawdown because it has now affected the soil underneath this shallow footing. So what can we do? Well, in practice, we have something called a recharge well point here. Recharge well points are in essence holes in the ground where we can pump water back in. And if you pump water back in, you might be able to shift this blue line back up here so that it doesn't affect the shallow footing so much in terms of consolidation. In theory, it sounds great, but in practice, it's very difficult to recharge water back in the ground. Particularly, it's difficult to control where it goes, let alone control the groundwater table. But you'll see observation wells, recharge wells used in construction projects in Hong Kong. So the main focus of this slide is telling us that anytime we do dewatering works outside a cofferdam, we have to make sure that we're not adversely affecting settlement outside of it. If you look at this particular slide, it just shows different combinations of well points, how you can use different combinations to draw down the water table to what you want. Initially here you have groundwater table, and let's say you want to work inside this excavation, then you can have a well point here, and you can suppress it just on one side. Likewise, if you want a more symmetrical final groundwater table, you can have two well points, and you can get some profile like this relative to the initial groundwater table and install two well points, having an extra well for redundancy in case the other one fails. Alternatively, you can also carry out the installation of well points at different depths. Just like your excavation in your capstone projects, you excavate your site at different times in your construction sequence. So you don't need to draw the water table down all at once. So you may have an initial water table here, and in the first stage sequence of your construction or your Plaxis analysis, you only need to excavate, perhaps, if we use a different color, you only need to, let's say, excavate to this point. Then stage 1 well point might be for the next stage, for example. Let's say we need to excavate to here, then we can activate this pump to drop it down. And if you need to go deeper, then you can, in sequence, keep on activating more dewatering wells. You can have a very deep one, and eventually just place your dewatering wells at the depth that would give you a suppressed groundwater table to enable you to do construction inside any excavation. So this is usually how the dewatering wells are designed on a construction site. The design of these drawdown curves and these drawdown cones are probably quite specific and maybe too much for the scope of this class, but there are approaches to estimate the size of a cone if you understand the permeability of the soil, and if you understand the capacity of your pump, then you can estimate how the drawdown cone looks like. By drawdown cone, I'm talking about this shape here. And then you can draw lines to predict whether your pumping arrangement will be sufficient for your construction site. So to summarize and tidy up this particular module, we have numerous dewatering techniques. We talked about sump and ditches. These are just very shallow, maybe 1 to 1.5 meter deep trenches, and then you throw a pump in and it takes out the water. You can have well point systems. You can have special types of pumps, vacuum well pumps. You can also have jet pumps. These are just different style of pumps. You can also go very deep in the ground. We call these deep well systems. And for very low permeability soil, you can use electro-osmosis. And the details are basically given on the right column under guideline on when you should use it, and the applications in the middle. So for electro-osmosis, we deal with fine-grained soils, less so for the coarse-grained soils. If you need to go very deep, we use deep well systems for deep excavations, and then you can use a combination of any other pumps for routine dewater. So this is just a summary for your reference. And that's all we will talk about for dewater. So I want to now transition to the final module of our course. And the final module is related to chemical means of ground improvement. Again, with chemical means, it's quite empirical again, and it requires a lot of experience to carry out grouting and deep mixing works in Hong Kong. To give you an indication of how empirical this is, I mentioned several times in our course that the third runway system of the Hong Kong International Airport was partially reclaimed using deep cement mixing. Now, Hong Kong did not have experience using deep cement mixing previously, and it's such a empirical type improvement method that we needed to ask for help overseas. For example, Korean contractors, Japanese contractors have experience with deep cement mixing for land reclamation. So we tend to have to rely on previous expertise. So that's why we mentioned that these approaches are highly empirical. And if you remember what I said earlier about grouting, grouting is a very difficult type of ground improvement to design for, because more often than not, we can't really see what's underneath the ground. And it's not uncommon to have unsuccessful grouting operations in the field. Let's say you want to improve hydraulic cutoff, increase the permeability or decrease the permeability of the ground. Even after your grouting contractor pumps in a lot of grout, and then you assess the groundwater tables around the site, you might realize that all that grout pumped in the ground probably still didn't work. And then you might be thinking, why did it not work? Well, it's difficult to say because we can't really see what's in the ground. We're not sure where the grout went. Maybe there was very high seepage into the site, you're adjacent to the sea, and all the grout was carried away. Maybe there was a fissure in the underlying geology, and all the grout got pumped into a fissure in the ground. So there are lots of uncertainties when carrying out grouting works, but notwithstanding, grouting is a routine geotechnical application used in the field to decrease the permeability of the ground, increase strength and stiffness. Now, another application of grouting is if you have a structure that is deformed because of earth movements, you can carry something called compensation grouting, where you try to alter the stresses in the ground to correct any movement of your geotechnical infrastructure. And we'll look at these various forms of grouting and deep mixing in this module. The reason why we combine grouting and deep mixing together is because I consider these two approaches a chemical ground improvement, is what we call. Why do we call it a chemical improvement? Well, we'll talk about it in a bit, because what we're doing is introducing binders in the ground. By binders, I mean cement, fly ash, slag, lime, anything that can be mixed with the soil to create a series of chemical reactions to increase the stiffness and strength and reduce the permeability of the ground. So that's why we call grouting and deep mixing chemical stabilization approaches. Now, there are a few expected outcomes for this last module. When we try to chemically stabilize the ground, there are two ways to do it. You can, as I mentioned, pump in some chemical mixture in the ground to fill in the voids between the soil grains. That's one way. The second way is you use some sort of rig with a mixing device on it, and you churn up the in situ soil and pump in binder at the same time. So there are, in essence, two ways to chemically stabilize the ground that we routinely use. So by the end of this particular module, the aim is for you to be able to differentiate between these two types of methods. The next objective is to somewhat understand the basic principles of how simply by putting in cement in the ground, we're getting enhanced strength and stiffness and reduced permeability. Of course, we cannot go into a lot of detail how the chemical reaction works, but I will go over the main reactions that happen in the ground. So, as geotechnical engineers, most of the time we just accept the idea that yes, if we put lime and cement in the ground, we expect the ground to strengthen. But today I want to talk about what are these chemical reactions that cause the ground to strengthen. I don't expect you to memorize any of these chemical reactions in detail in terms of formulation, but we should still know the main mechanisms. For example, dehydration, which we'll talk about later, ion exchange, pozzolanic activity, also cement hydration. So these are the main mechanisms that give us the strength that we see after mixing binders with soil. You can probably imagine already that as a contractor, chemical stabilization of the ground is difficult. if you played with concrete in your concrete class, you probably remember that concrete sets under a certain time. So if you don't get your ground improvement work done, or the injection of grouting in the ground done in a timely manner, your grout can set. Also, if your grout doesn't set because of the mixture you use, it'll get washed away by any ground movements, groundwater movements that is in the ground. If your grout mixture is too thick, it won't be able to permeate far enough in the soil, and you'll get a very limited range of improvement. If your grout is too viscous, it's going to go very far but have no strength. So it's quite delicate, grouting works. That's why we really rely on expert contractors to carry out routine grouting works in Hong Kong. So being long-winded, we want to discuss the basic principles for gaining strength. We'll look at some of the main binders. We can't look at all of them. Maybe just cement and lime, perhaps. We use these as examples because the basic mechanisms for obtaining strength are more or less the same. The third objective is to be able to pinpoint what scenarios in the field call for grouting or deep mixing. When do we need to carry out these chemical stabilization approaches? The next one is, how do we describe the different types of grout techniques? When do we use them? What type of soil? What are their advantages? What are their disadvantages? So we'll try to look at the different types of grout approaches. Now, some of these grouting approaches are almost a hybrid between deep mixing and grouting. For example, jet grouting is almost like a hybrid between deep cement mixing and grouting. So you'll quickly understand why I say that later on. There are also a wide range of grout mixtures. If you can imagine what I mentioned earlier about different viscosities, different setting time, different strength, ability to use up in situ water, you can basically control this by using different types of grout mixtures. A lot of the time, the grout mixtures are controlled by or dictated by what the particle size of the binder is. The smaller the particle size of the binder constituents, the more flowable your grout will be in the ground. Then you can move through less pervious soil. For example, if you have fine-grained soil and you have very fine-grained binder particle sizes, then this will be advantageous for you because then your grout mixtures can travel much further into the ground. The fifth expected outcome is we want to be able to describe what compensation grouting is, jet grouting, as I mentioned, permeation grouting. Also, there are common misconceptions in the field. Some people call it TAM grouting. The TAM grouting is not really a type of grouting, it's just a pipe. It's a special pipe to help you inject grout at a target elevation rather than have it in an uncontrolled manner. So we'll talk about the different types of grout injections used commonly in Hong Kong. Of course, following that, I mentioned already, is the TAM pipe, what it is, why we use it in Hong Kong, why we use it in grouting in general. What kind of control does it give us? What type of advantage does it give us if we use the TAM pipe versus we don't use the TAM pipe for grouting? So the top, perhaps 6 expected outcomes are mainly related to grouting. There isn't a lot of fundamental difference in terms of the mechanisms for obtaining strength between deep mixing and grouting, but we will talk about the next part after these 6 outcomes, particularly deep mixing. Deep mixing seems to be a hot topic these days in Hong Kong because of the success of the third runway system and also its increasing use for new reclamation projects in Hong Kong. The new Dong Chung extension has also successfully used deep cement mixing to improve the ground in various areas. And there are 2 terms that you see at the bottom, second bottom, last. Bullet point, wet and dry, deep mixing. I want to be able to express what they are, what their differences are, when we use dry, when we use wet deep mixing. We'll talk about that later on. Last but not least, I do want to spend some time to end off this module explaining some of the historic reclamation projects in Hong Kong. I found a lot of interesting multimedia on the internet talking about major reclamations that have defined Hong Kong. For example, the airport we use today was entirely reclaimed, and all the infrastructure leading up to that new airport, particularly the roads, the bridges, the piers, tunnels, a lot of it relied on reclaimed land to carry out. We'll also look at documentations of deep cement mixing for the third runway system, so you have a sense as to what it looks like. So these are expected outcomes of this particular module. So the first thing we have to do is define grout. What is grout? Grout is a mixture of water and binder, basically. And we inject these pumpable mixtures of water and binder into the ground. We can also add chemical additives to change the flowability of these mixtures. And the ultimate goal, there are three ultimate goals for grouts. Strength and stiffness are 1 and 2. The last one is to decrease permeability. This is commonly used in Hong Kong, to decrease permeability for grout coatings that we talked about. Grout can also be used to correct mistakes in ground movements. By injecting grout under high pressure, we can correct maybe some tilting. We can also use grout to underpin structures. What do we mean by that? Let's say you have a pile that's resting on soil and we plan to excavate underneath the toe of this pile. What we can do to ensure minimal movement of this pile that may be supporting a building, bridge, is we can grout it underneath. We call this underpinning earthwork structures. We can also use grouting in cofferdams, embankments to improve hydraulic cutoff as we need. Now, so there's a wide range of use for grout in geotechnical engineering, and you'll see this very quickly when you start working in the geotechnical practice. In fact, grout is so routine that even when we finish drilling a borehole for GI, we have to grout it again to close it off. Otherwise, we have a giant hole in the ground, right? So grouting is very routinely used for soil nails. All sorts of geotechnical structure rely on grout. Why do we use grout though, you might be thinking? It seems like it's quite complicated, there's not a lot of control. Well, at the bottom of the slide here, we have listed some advantages and limitations. Grouting is the mean by which we drill a hole and then we place a pipe in the ground and we inject a mixture, chemical admixture in the ground. The purpose of doing this is we want to minimize ground movement. We don't want there to be any stress release. If we have to excavate, you create stress release, whether you like it or not. And stress release causes earth movements, and that can affect infrastructure nearby. So grouting is good in that all you have to do is drill a hole, inject grout, and it's quite minimal and not so expensive. You can also drill holes quite easily. They don't have to be vertical, they can be vertical as well. So as long as you can drill a hole to something, you can inject grout there. And drilling holes is quite easy if you have special rigs to do it. You don't really need a lot of head clearance either in a particular site. And you'll see later on that the entire setup required for grouting is quite economical. You don't need any big tools or plants or machines to use. So these three things listed here are perhaps the advantages of grouting. Limitations, there are quite a few. I mentioned one already. After a grouting operation, you're not really sure if it worked. you have to wait a while, right? And if it worked for, let's say, hydraulic cutoff, you'll see benefits. If it doesn't work, there's really no explanation sometimes. What do you do? Is there claims against the contractor, for example? Was it really their fault? Were the ground conditions unknown? So there's a lot of uncertainty when we deal with grouting. And grouting under very large areas at a wide variation of depths may not be that cheap, actually, if you have very large volumes. And the first bullet point says area of improvement is sometimes uncertain. What do we mean by that? We mean by, let's say you have a simple excavation, and we looked at this case a few times. Let's say this red part is rough, and it's quite competent, and it's quite impervious. So let's say we have some flow lines going like this. You may design, as the geotechnical engineer on site, as the engineer on site, some sort of grout curtain here to, you might not want complete cutoff, you might want to just increase the path that the water has to travel, right? To help suppress this water table inside the site. But what I mean by area improvement is unknown is, let's say your design was, yes, our curtain will be 1 meter thick and 2 meters in depth. You can't really validate this, right? After the contractor comes, they can try to do this, but you might get something, let's use another color, you might get something that looks like, you might get something that looks like this, or a small blob here, or it might be really big, or it might not be able to serve the same shape, because we can't really see the geological conditions in the ground. So after the contractor pumps in the set amount of volume, we can estimate the volume, right? We know the curtain is 2 meters long, 1 meter wide, and we know the span into the page. So we can estimate the volume of replacement, because we can estimate the void ratio in the soil from our ground investigation. So let's say we're supposed to inject 50 cubic meters of grout in the ground. We keep track when we inject the grout in the ground, but where this 50 cubic meters of grout goes sometimes is not easy to control. There can be other issues with grout. You could also be, if I close this excavation off, you can also be, actually right beside, you can also be right by the sea, right? If you're right by the sea, what happens? Well, you might get some seepage and flow lines here that, as you're pumping into the ground, some unknown underground hydrogeology is carrying your grout somewhere else. So your grout could end up maybe forming a weird shape over here where you didn't want it to, right? Because there's some underground seepage. So these things are hard to estimate and control with grout. So that is what I meant by area of improvement is sometimes uncertain. The second limitation is grouting may cause ground improvement and distress to existing structures. Well, what do we mean there? Well, we have to inject grout at high pressure in the ground. Why do we have to do that? Well, if you don't, you won't be able to squeeze the grout into between the voids of the soil. So we have to intrinsically inject it at high pressure. Now, high pressure grout into the ground may cause additional stresses And additional stresses will cause ground movements, and it might deform sheet pile wall. It might cause ground movements in unexpected locations. So grouting is inserted at high stress into the ground. So that's what we meant by distressed existing structures. This third one is less of a problem these days. In the early stages of grouting for geotechnical improvement, there were chemical additives and superfine grouts that had adverse effects to the environment, but this is not so much an issue anymore. We've ironed this out mostly. We don't use anything that's creates adverse effects to the environment. Last but not least, I mentioned this several times already, you need a specialist contractor that's very familiar with local geological conditions to carry out grout operations. And the KPI to assess whether grouting is successful or not is shown in the yellow box. You need to be very experienced and understand what grout mixture to use in the first place. And how do you know that? Well, you'll see later on, we need to understand the permeability of the in situ soil. We need to understand what size certain binders are. Will they fit into the voids of the in situ soil? We also have to know the soil type. Different soil types may have different reactions to your grout. And the method of injection is important. For example, are we permeation grouting, where we're trying to squeeze the grout in the voids? Are we doing compaction grouting, where we just displace all the in situ soil aside? So the effectiveness of grout operation depends on these three factors predominantly. Grouting has been around for a long time. Grouting did not come from theory, and you can probably surmise that based on what I've talked about. It's based on experience. So grouting has been going on since the early 1800s, and we probably find evidence of grouting even before that. Using chemical means to stabilize the ground is nothing new, if you remember our first lecture. There are historic evidence that our ancestors understood that if you mix lime with the ground, it stabilizes it. So systematic use of grouting, however, for geotechnical applications is more recent, and you can see that we started off using clay grouts to reduce the permeability of the ground. Then we use cement. Cement's interesting in that it reduces permeability, increases strength and stiffness as well. Then we advance to chemical grout. What does that mean? Chemical grout has very fine particles, so then we can start grouting in very impervious soils, and the grout can permeate much further into the soil. However, there were environmental concerns with the type of admixtures used. Now we have modern grouting after 1970, and everything is quite mature. We're not too worried about environmental concerns. We've also developed many different types of injection techniques, TAM pipes, permeation, compaction, compensation. Jet grouting is even more impressive, a new tool that we've developed over recent decades. So the main point, nevertheless, is grouting is not something that came from theory. So you're not going to expect to find some analytical equation to calculate the ideal grouting design. It's going to rely on trials. Just like when we created the deep cement mixing columns at the third runway system, we have to carry out trials on site to see if this mixture, this pressure works. And then we can perhaps do a CBT or SBT test to check. So sometimes grout requires trials. There are significant advancements in grouting. I mentioned in the early 1800s was when the first instance of grout was used, and a clay type grout material was used, so nothing too fancy in terms of using cement or fly ash or slag. It was just a simple clay water mixture to repair a sluice gate in France, and then further in the early 1911, cement grout was used to correct a shaft that was sinking. And then in the 1920s, or nearly 1920s, a different mixture of asphalt grout was used. And then progressively, we see more and more chemical grouting applications that are finer and finer in particle size and enable us to have grout travel further and further in the ground. So these are just some examples of grout development. And it's nothing really high tech, right? I mean, we've been using it since 1800s, and we're still using the same technique. So not much has changed since the early times. There are different types of grout materials, and the type of grout material really depends on what the permeability of your in situ soil is. The most commonly used grout mixture is what you see at the top of the slide, cement grout. Cement grout is really good for coarse-grained soils with very high permeability, sand, gravel. It's used for infilling cavities. For example, in some scheduled areas in Hong Kong, you might be worried about karstic geology or huge voids. So if you detect these voids, what can you do? Well, then it becomes easy to just put a pipe down in your void, inject some cement grout in there, and let the cement set, and then it fills up the void. Also, cement grout is used to, as I mentioned, to fill up drill holes. We also use it to fill up some caves, maybe for mining as well. So cement grout's quite versatile. It's quite predictable, but it's only for highly pervious ground for most cases, unless you try to correct it with some additives. Another type of commonly used grout is a bentonite grout. It's used mainly to create an impervious curtain or barrier. It's, well, as you expect, bentonite is clay, right? So it's produced from clay and water, essentially, to create an impervious boundary. So that's bentonite grout for cutoff purposes. Then you have chemical grout. We talked about chemical grout a few times. We use a sodium silicate, calcium chloride to mix it together in liquid form, and these chemical grouts allow us to travel in medium grain soils. So slightly lower permeability. And as we move down on the slide, we have bitumen type grout. These are using petroleum products, mixtures of different chemical additives, and with the advent of bitumen related grouts, we're able to grout in fine grained soils as well, fine sands, and we're able to create cutoffs using bitumen. Now, the last type of grout material is a resin grout. Resin grouts are perhaps the finest in terms of the size and its ability to permeate into soil. And we use this with fine grained sands. You can have acrylic based and phenol based. Acrylic base is for strength and phenol base is for water tightening. You'll understand more of these things as you work in practice and you hear these terms get popped up. But this slide, in essence, tells us the 5 types of grouts commonly used in geotechnical works. If you want to summarize this slide in one diagram, then that would be the one at the bottom of the slide. We can see that there's 5 types of grouts that we talked about, and you would use the grout type towards the right of the flow chart, from cement slurries to resins, as your soil becomes less permeable. So from coarse grain to fine grain, you would try to progress towards the use of resins, bitumens, and chemicals. For routine geotechnical works, we tend to see cement and bentonite suspensions used in Hong Kong. So these are the 5 types of commonly encountered grout materials in the field. I mentioned the word groutability because it has to do with various parameters that tell you whether your grout will actually go into your soil. If your grout cannot permeate in your soil, you'll have to use very high pressures to inject the grout in, and you might just blow up the soil. The pressure that you use to inject the grout should not be more than the overburden provided by the soil. Otherwise, you'll cause heave in the ground and you'll blow up the ground. So that needs to be something you need to be aware of, the overburden pressure, the depth that you're injecting. Otherwise, you'll have heave and blowout. So groutability mainly depends on what? It depends on the void size of your soil and the size of your grout. So if you know the permeability of your soil from geological or ground investigations beforehand, then you can use this information to design the type of grout mixture that you'll use. Groutability just refers to, can you put the grout in the ground? Groutability depends on these 4 points that I've shown you. What's the nature of the ground? Is it fissured? Is it highly heterogeneous? For example, are there lands of clay sandwiched between very pervious layers? More importantly, what's the void size? The void size can be used to describe whether a particular type of grout can fit in the void size. What's the grouting injection method used? What's the pressure required? And then lastly, what's the grout composition? So groutability is really dependent on a very high fidelity ground investigation beforehand. If you don't know what the soil is in the ground, it's very difficult to design a good grout mixture. There are a multitude of empirical criteria on groutability. You just see some of these at the bottom. If you can carry out a particle size distribution curve of the soil you're grouting in, then you'll know what D15, D85 is. This just means the 15 or the 85 is just a percentage for passing, right? Mass passing for a PSD curve, right? When we have PSD, we have the shape of a PSD, then we can draw what's 50% passing, what's 85% passing, 10%, 95% passing. So you can extract these from your particle size distribution curves, calculate the ratios, and it'll tell you whether you can grout. So there are, of course, empirical criteria that tell you that grouting is always possible or grouting is not possible. And these are not theoretical in any circumstance. So at the bottom of the slide is just some criteria from Mitchell and Caddy. It's not something that is fixed. It may depend on your site conditions as well. So that's what groutability means. We talked about why particle size is so important when assessing groutability. Well, this particular diagram here helps advocate that. If you want to understand what the effect of particle size is on grouting, we can almost treat this particular slide as to scale, at least to relative scale, okay? At least the different types of particle sizes are to scale relative to each other. So at the top of the slide here, you can see that this is a typical medium-grained sand, about 2,000 microns. We have a piece of fine-grained sand here, about 850 microns. To give you a perspective, this is the cross-section of a human hair, 100 microns. And these are different types of binders that we can use. So this is type 3 Portland cement, there's type 1, 2, 3. Compositions are more or less the same. Fly ash is another type of binder we use. These are just byproducts from industrial processes. We have microfine cement. Microfine cement may be very good for getting into very impervious soils. Then you have clay here. It's 2 microns. So by looking at this, you can probably guess it's very difficult to permeate grout into clay, right? Just given the size of how microfine cement is 10 microns, and a clay particle is 2 microns. Underneath, you can also see other types of geomaterial. We have silt, and then we have ordinary Portland cement, which is quite large, 70 microns. Now, if you want to fill in fissures in the ground, at the bottom is an example of some sort of fissure or crack in the ground between 2 masses of rock. And the fracture is about 0.05 millimeters. If you use micro cement, you'll be able to permeate into this fissure, because microfine cement is 10 microns, right? But if you use ordinary Portland cement, you're not going to be able to permeate into your fissures. So the lesson of this slide is you have to know the size of your fissures and the permeability of your soil or the void ratios involved before you can grout. So I hope this is an interesting slide to show you the relative size and how to choose the correct type of binder to use. Other types of binder, slag, lime, quicklime, these are becoming interesting alternatives. One that is being explored by authorities locally is GGBS. Is it GGBS for granular, is it ground blasted slag? Something like that, GGBS. So it's, why is GGBS good? Because it has a very low carbon footprint or embodied footprint. Cement is actually has a very high embodied footprint. That's why we try to minimize the use of cement these days in geotechnical infrastructure. You can probably imagine in deep cement mixing, the term DCM, the C stands for cement. So you're inevitably injecting a lot of cement in the ground. It's actually quite appalling how much cement we're using for ground improvement. If we try to calculate the embodied carbon footprint of a land reclamation, it could be quite intimidating. So these days, researchers and governments are looking towards using alternatives rather than cement. In fact, for the third runway system, I understand that at one point during the peak of the reclamation, we were using a substantial percentage of the global cement supply as well. So I guess most of you in this room are the next generation of engineers. So see if you can propose alternate binders. GGBS maybe. Try not to use so much cement to reduce the embodied carbon footprint of geotechnical infrastructure. So that's an alternative we can use and think about. So to give you an indication of what groutability means, let me show you just a video. So we have three types of grout material. We have cement mixture poured into this granular material. We have in the middle acrylic. Remember I talked about acrylic? Phenol base, so this is the acrylic. And this is just water on the right. So to give you an impression about what groutability looks like using different materials. So we're pouring the three mixtures in. You can see on the left, the grout is just standing on top of the granular material, but the acrylic material basically permeates the entire soil right away in the middle. The water, of course, is quite pervious, but the only difference is the acrylic material gives you strength. You can lift up the material in the middle. The left case here for the cement, I wouldn't consider this not groutable, actually. This is not really a good example because in the ground you would have substantial overburden and confining pressure on top. So you could inject the cement slurry at a higher pressure and try to permeate it through the granular material. So this is an example of groutability of different materials involved. So if you missed it, I'll show you it again. So here's the standing cement grout. It's very difficult to permeate it. Look at how fast the acrylic permeates the entire beaker here. Water has done a pretty good job, but the only difference between water and acrylic is you're not getting strength for the water, but you'll get strength for acrylic. Cement, on the other hand, will give you strength, but there's a setting time, right? It requires time to get strength, and it requires pressure to permeate into the granular material. So that's what we mean by groutability. Now, there are different circumstances for using different types of grouts. Here, on this table here, we can see that the types of grout is listed on the left side. We have cement, bentonite, some sort of bitumen. The bitumen, underneath we have silicate and resins. You have acrylic, that's the one we saw just now, the acrylic. And W and S stands for, do you want to use the grout for increasing the strength of the soil or do you want to use it for reducing permeability, what we call water tightening? So you can look at this here, and then you can look at underneath the different permeability of the soil. Depending on the type of soil involved, there are constraints. For example, for silt material, you have 10 to the minus 6, 10 to the minus 7. It's very difficult to get into clay as well. There are also implications on the working range. So you want to be in the horizontal or diagonal hash range. If you're in this very sandy range, you're probably not going to use that particular type of grout because of cost problems involved. So these are the sandy regions where you wouldn't use that type of grout. Cement, as we talked about, is very good for low permeability. Bentonite is good for coarse grained sands towards medium grained sand. Bitumen is good for all types of sand. Silicate gel is for medium grained sand, and resins are for fine grained sands. So if you want to know the type of application for different types of grout material, you can make reference to this particular table here. Let's take a short break. I think we're quite exhausted. So let's take a 10-minute break, and then we will continue again.
由零開始，從零開始學，我都唔識，快抄都唔識。
All right, let's carry on. Yeah, I remember there were some slides on standpipes and piezometers. I'll upload that. Some of you are telling me that you drew them. So yeah, I'll upload that after this lecture. Sorry about that. Let's carry on. So actually, before I talk about this, I want to explain the basic principles of strength in grouting. Well, let's finish this slide first. So you can probably expect that the more water content you have in your soil, the more reduction in strength that you see. So what you see on this graph here is on the y-axis compressive strength. Normally when we talk about grouting, we carry out unconfined compressive strength tests, so UCS test. Even for deep cement mixing, when we take specimens from the ground and we take cylinders, we bring it back to the lab and carry out unconfined compression tests. So the compressive strength here is referring to UCS, and the UCS depends on the strength. It's just like concrete. You can take it 7 days, 14 days, 28 days. It depends. But the main point we want to mention from this slide is that as you increase the water to cement ratio, we see a reduction in strength. Why is that? Well, to some extent, we want to dehydrate the soil when we mix binders with the soil. By dehydrating the soil, we can increase stiffness and strength. So we'll talk about that in a bit. If we increase the water content, we also get improvements in terms of flowability. The grout can travel a bit further, right? It becomes more watery. So there's a trade-off between the two. You can also see that in the middle here, this line here shows basically resistance to flow. As we increase the water to cement ratio, meaning that we increase more water in the mixture, there's much less shear resistance. And less shear resistance means your grout can travel much further into the soil. So let's talk about some of the mechanisms of strength first. Okay, so you might be curious why mixing grout in the ground, not grout, why mixing a binder in the ground gives you strength. Let's talk about, that's a bad color. Let's talk about the basic principles. Of strength gain from using binders in soil. So there are a few mechanisms. The first mechanism is hydration of binder. For this first example, let's use lime as an example. Let's use lime, and then in the second one we can talk about cement. So for hydration of binder, what happens is, let's say we have lime. Lime is basically COA. Don't worry, you don't need to memorize any of these chemical formulations. By hydration, what do we mean? H2O is water, right? We want to mix our binder with water. That's why we call it hydrating. We want to hydrate, just like when we drink water, we hydrate ourselves. So lime. So when we hydrate lime, the chemical reaction we get is CaOH2, and it becomes exothermic. We get heat as well. What is the function of the heat? Well, the heat reduces, you can treat it like it's drying the soil out, right? Reduces the moisture in the soil. And by reducing moisture, we increase the strength of the soil. So that's the first reaction. The first mechanism is called hydration of the binder. When we mix a binder with water, we generate a chemical reaction that's exothermic, meaning that there's heat, we reduce the moisture, and by reducing some of the water, we get slight improvement in strength. So this is one mechanism. Now, the second mechanism is called ion exchange. You can see from the chemical formula from the top, when we have hydrated lime is this here. This hydrated lime will dissolve in water, and when it dissolves in water, we get to break down the CaOH2 into its constituent ions. So we get these two, right? When we break down the hydrated lime. These ions here exchange with the cations on the surface of a clay. This process of ion exchange is unique and helps increase the strength as it changes physical properties of the clay. What do we mean by properties? Well, it changes the plasticity. Reduces the plasticity. This plasticity is not the same as when we're talking about elastoplastic, okay? Plasticity means moldability. Can you mold this material? Sort of like a Play-Doh, right? Now the ion exchange is quite interesting. The ion exchange here, particularly the hydroxide, will, this one here, this will create a high pH environment. So remember pH, basic acidic. So under a high pH environment, clay, which has clay, which has silica and aluminum, dissolves in the water to have a reaction with the Ca2+ ions that I talked about. And this here will form two things. The first one is calcium silicate gel. The second one is calcium aluminate gel. This reaction in the red here is our third mechanism in the red text. This third mechanism is called pozzolanic reaction. Pozzolanic reaction is the formation of these two types of gels here. And these two types of gels will increase the strength and stiffness of your soil overall. These gels here, these two gels, calcium silicate and calcium aluminate, will remain stable as long as the pH in your water doesn't drop, right? So, I'll write it here. The two gels will remain stable as long as a high pH is maintained. Now, this is interesting, the last one. So there are three mechanisms. The first mechanism is hydration of binder, right? The second one is ion exchange. The last one is pozzolanic reaction. Why is this interesting about maintaining stable pH? So then the question we ask is, what happens if the pH is not stable in the marine environment? What if the pH changes? Does this have adverse effects on the strength of cement stabilized soil? So these are perhaps interesting things we can look at. For example, in the future, what if the pH changes because due to climate change, right? The pH of the oceans can also change. How does that affect chemically stabilized soil? So what I've shown you here are the basic principles of strength gain for lime. But these three mechanisms, hydration of binder, ion exchange, and pozzolanic reaction are the same for nearly all binders. Now, the only difference if we use cement is you'll also see hydration of the binder. It doesn't, I think it's strictly necessary to talk about all the chemical formulations because you don't have to memorize any of that. We just need to know the mechanism. So the first is if you hydrate a binder, you generate heat. Heat will reduce the moisture in the soil. By reducing moisture, we get strength. By hydrating the binder, you create ion exchange between the clay and the hydrated binder, which is the hydrated lime in this case. It changes the pH in the environment, changes the physical properties of the clay, and ultimately, this leads to pozzolanic reactions to get gels, right? You get two types of gels because clay has silicate and silica and aluminum. So these are the three main mechanisms. Now, let's say we were to look at cement. So let's say this is cement now, not lime. This is another type of binder, the most commonly used type of binder. So we have cement. So cement, we would also get these mechanisms that we talked about. Hydration, binder. So why am I going over this? Because I don't want us to just think, yes, we put lime in the ground, soil is improved. I want us to sort of understand the mechanisms involved as well. So hydration of binder also has ion exchange. And it also has the pozzolanic reaction. Pozzolanic reaction. Except cement has an additional one. It has something called cement hydration products. So this is the one the lime doesn't have. Now, Portland cement types 1, 2, and 3 are common types of Portland cement that we use. So typical Portland cement is the type of cement we use, right, for construction. It has basically 4 main types of compounds. Has what we call a tricalcium. You don't have to remember any of these names. Silicate, dicalcium silicate, tricalcium aluminate. Also has a tetracalcium aluminate. So this is a compound, and if you're interested, chemical formula. Causing nightmares for those of you that did not choose chemical engineering. Chemical formula for tricalcium aluminate is tetra. So the percentage by weight or typical, I think this is the same or very similar for types 1, 2, and 3 Portland cement. We're talking about maybe 40 to 65%. This one is 15 to 35, 5 to 12, 6 to 10. So why am I showing you the composition? Well, let's take a look at the most dominant compound, which is the tricalcium silicate. So that's this one here. So what does it mean to have cement hydration products? Well, let's take a look at the most dominant one. 40 to 65% of it is this first one here, tricalcium silicate. So this is a balanced out chemical formula. This is hydrating cement, okay? So if you remember this from the previous lime example, let's talk about this one first. This is calcium hydroxide. It's also in the lime example I showed you on the last page. It is also released from this chemical reaction to contribute to osmotic reaction. But this is not the one we're interested in. These here we call this the cement hydration byproduct. And this is the special byproduct that gives us increased stiffness, increased strength, and the hardening effect. So to enable the soil binder mixture to set. So on top of what you saw for lime here, this cement hydration product is just this one here. So I tried to keep it as simple as possible. You don't have to worry about the chemical formulas, but there are these mechanisms. Hydration of binder, adding water to a binder, can cause exothermic reaction. Ion exchange, osmotic reaction causes gels, and then cement hydration product also creates a special product at the end. So these are the processes that give us strength when we mix in binders in the ground with strong water. And there's no difference between grouting and deep mixing. The same reactions take place to give us strength, and that's why we mix binders in the ground to improve strength. So this is just a sidetrack. So we can shift back. So in case you weren't sure about what's happening when we mix binders in the ground or why we do it, I tried to explain as simple as possible. There's a few mechanisms that take place chemically. So it's called chemical ground improvement, so that's why they're chemical formulas. And it also helps explain some of these things here in terms of change of strength with reduction in cement ratio, right? So that's in terms of strength. That's what happens when we mix binders in the ground. Now, aside from strength and stiffness, some other things that a geotechnical engineer that's designing a grout design needs to consider. We need to consider whether something can flow in the ground. And if you recall from your fluid mechanics, we also care about the rheology of the flow. What's rheology? Well, the rheology is the shear resistance of a fluid at different shear rates. So we can treat a grout if it's a coherent suspension of binder and water as one coherent single fluid. And if we do that, then we can start to characterize the rheology using rheological models. Newtonian, we're all familiar with, so it's a linear relationship between the shear resistance and the shear rate, right? So water is Newtonian. You can also have Bingham. Bingham means that there's just some yield stress you have to overcome before something flows. So grout is definitely not Newtonian because it has shear resistance. And as we increase the content of grout binder material, the viscosity increases and also the yield stress before it flows increases. Why do we care whether grout flows or not? Well, we need to permeate it. If we're carrying out permeation grouting, we need the grout to travel some distance. We need the grout to travel down the pipe from our mixer into the ground. If it doesn't flow, you're going to have a very difficult time getting the grout from your mixer into the ground. So there are different rheological models in hand to describe rheology. And the Bingham one in this case is not much complicated than Newtonian. It's the same one as Newtonian here, except there's a yield stress here. So that's the only difference. Now, this is just a flashback from your fluid mechanics days. Rheology is just a description of shear stress, tau, over shear rate, gamma dot. And depending on the grout engineer, you may want to design your grout mixture to have different types of rheology. For example, if you want the grout to flow very freely in your fluid, you don't want it to have any yield stress, you don't even care if it settles or not, then you can design it to be like a Newtonian fluid, right? If you want your grout to somehow set when it has a lower pressure, a lower velocity, then you might want to deal with something such as a Bingham suspension. So bentonite grout is like a Bingham rheology. There's some yield stress to get it to move, and if you don't have enough stress, it'll just come to rest and set. There are of course other types of shear thickening and shear thinning. This dilaton one, we call it shear thickening. Pseudoplastic is shear thinning, meaning that it'll get more and more water-like as you shear it at higher rates. So these are common rheological models used to describe grout. And we can evidently, in the lab, measure the rheology of our grout before we go to the field. So this should be done as a check to make sure that the rheology that you design can be injected into the ground. So to try to understand rheological behavior of grouts, let me show another educational multimedia. So
digital lesson. Today, we're going
So the first one is we can also design grouts to be nearly have no yield stress. So that would be very Newtonian-like, right?
to take on the interesting topic of Newtonian and non-Newtonian fluids. A classic Newtonian fluid is water. Water has a very
So
predictable
this would be a
viscosity.
very pervious acrylic resin that I showed you earlier. When we poured it on the soil, it just permeated, just like the water one beside it.
Newtonian fluids also have predictable
Well,
temperature
Newtonian fluids, as
pressure
this
changes.
guy says, is very predictable, right? We have a linear
To
change.
investigate the properties of Newtonian
in
fluids
rheology.
experimentally, let's start with some warm honey. As you can see here, warm honey flows easily.
So warm honey
and
has a
will
much
easily
higher
flow around
viscosity,
objects,
and it may not
such
be
as this
linear
fluid.
in shear
Placing a
resistance over
force
shear
on the
rate.
honey has no effect on its viscosity. Even if we place a large force on it with a hammer, the honey predictably flows around the hammer.
So it's not so much shear rate dependent, right?
If we try the same thing with cold honey, we see, as you would expect, the honey is more viscous. That is, it flows slower. But when we test it with the ruler, we see it behaves much like the warm honey. It's the same when using the hammer.
So why are we showing you this? We're trying to show you that just like grout, fluids are shear rate dependent. Depending on how fast you shear it, by putting in a spoon or a ruler, you're actually shearing the fluid, right? And when we pump grout in the ground, we're also shearing it.
Applying a force has no effect on the viscosity. Honey, whether it's warm or cold, is a good example of a Newtonian fluid. Let's try a different fluid. We'll perform the same
So
test
some
with
grouts
cornstarch
can behave
solution.
like this mixture
When you
here.
pour this solution, it appears to behave much the same way as the honey. When you place a ruler into it slowly, the fluid flows around the ruler. However, when you attempt to force the ruler into the fluid instantly becomes more viscous. Hammering the fluid with even more force produces even more resistance to flow. Because a cornstarch solution's viscosity changes with an applied force, It is a non-Newtonian fluid. Unlike a Newtonian fluid, applying forces to this non-Newtonian fluid causes its particles to behave more like a solid. This makes the behavior of non-Newtonian fluids very strange.
But this is very
As you
similar
can
to what
see
a grout
here,
mixture may look
even
like
though
in the field.
cornstarch solution flows when emptied from a bucket, you can't break its surface even when using a sledgehammer. You can even jump on and off a cornstarch solution. Just remember, don't stand on it, as you will eventually sink.
Okay, so why are we
So in
showing
summer-
this? We're showing this because when we're carrying out grouting operations in the field, we control the rate of injection using pumps. So it's imperative to understand the rheology of your grout mixture. You have to measure it before you go to the field. Otherwise, if you inject it at high pressures, it's the same as what you see in this video, applying very high shear rate to your specimen, and it will have very low groutability. You won't be able to get it into the ground at all. So grouting can be quite complex if you have to consider the rheological behavior of your grout as well. Yeah, they're going to show you how this mixture looks like more, but I think you get the point. So that's the last thing we have to care about when we design grout is the rheology. Of course, we can only give you a very superficial understanding of it, but flowability is also an important variable. Now, there are some key KPIs, key performance indices to describe an ideal grout mixture. First of all, is it stable? For example, is it just like the cornstarch fluid we talked about? If you change the velocity, meaning the shear rate slightly, it just becomes, its strength hardens significantly. You can't get it to flow. That's probably not what we want. We want a stable mixture that has a very wide working range, so that when there are variabilities in pumping, when you want to pump faster, pump slower into the ground, you have a very stable and consistent injection. You also may want low viscosity. Why is that? Well, low viscosity gives you more permeation in the ground. You can get a further improvement area. There are circumstances when you don't want improved area because you want very high viscosity. It's a type of grouting called compaction grouting, where it's so thick you're just displacing the soil around it as a pressure bulb. So that happens as well. You want to have controllable setting time as well. You need to know when the grout will harden. So that will tell you when you need to stop your grouting operations, or let's say you know the grout will set in 1 minute. So you need to finish your grouting operations within that 1 minute window. Otherwise, everything will set, including being stuck in your injection equipment as well. Well, this one is not always a characteristic, but depending on what the use of the grout is. If the use of the grout is for strength and stiffness improvement, then you want high strength. This can be tested out in the lab beforehand by doing unconfined compressive strength testing. These days, we're not so worried about non-toxic. There are resins that may not be so ideal for the environment, but these have mostly been purged out of general practice. You want to make sure your grout can last. It doesn't get eroded easily. We talked about one of the mechanisms of strength is controlled by the pH, right? You don't want a slight change in pH to affect your silicate and aluminum gels, your pozzolanic reactions, right? That is what we would call not permanent. Not permanent would also mean, can it withstand the seepage underground? If you're right beside the sea and you're trying to create a grout curtain or improve the hydraulic cutoff, if there's very high discharge from the sea, will it erode your grout that you put in the ground? So these are considerations of an ideal grout. Last but not least, you want to minimize the use of very expensive binders, expensive additives. Grouting at the end of the day is just pumping in some admixture to the ground where you may not have full control of where it's going. So you don't want to do this in excess volumes and in an uncontrolled manner, so it should be a cheap mixture to use. So, how do we inject grout in the ground? Well, we mentioned that it's very simple in terms of equipment. That's perhaps why grouting is advantageous in geotechnical engineering. So we've taken this diagram from the Geotechnical Engineering Office Manual. You can see a few things here. So normally we have a grout mixture. We can have a valve here with water. You can pour in the grout material, the binder here, and they'll mix everything out together, the water and the binder. And then you can have some sort of pumping device, bring it to the agitator to disturb it continuously. Why is there an agitator? Because just like a concrete truck, if you don't continuously stir the grout, it'll set, right? So you need a device that continuously mixes your grout mixture so it doesn't set and harden, right? Because you need some time to carry out your grouting injection in the ground. So normally we would have an agitator, and the agitator keeps it in a coherent mixture that increases the flowability. Then from the agitator, what happens is you have a pump. Now the pump here can help provide pressure to get through these channel of pipes here into the injection point. Normally you would have flow meters. Why do we need flow meters? Like I said, before we grout, we already can come up with a design volume. We should always know how much grout we put in the ground, because you could be losing grout. Grout could be escaping into fissures, cracks, very pervious geological layers that you didn't know existed. And then there are two things. You might have to stop because you're not sure where the grout is going. It's not improving what you want to improve, and you're losing grout, which can be expensive for a particular operation. So the flow meters help to dictate how much grout is actually going to the ground. Is it similar to the design volumes? If it is, then you're happy with it. If it's not, you need to assess where is your grout going. It's not going to the target location. So on top of these flow meters, you're measuring it, and eventually you have a valve here that enables you to turn on and off, and the grout will just go into your designated location in the hole. On this grouting mechanism here, you also have pressure sensors. So you know the pressure that you're injecting the grout into the ground is. You can increase the pressure by adjusting parameters on your pump. And as I mentioned, the pressure sensor will also help to make sure that your grout injection pressure does not exceed the overburden pressure, because you'll blow up the ground with the grouting operation. So there's also some instrument here we call TAM pipe that we'll talk about later. We can use a TAM pipe to help us control the very specific elevation we want the grout to go out at. And that can be an additional accessory attached to this point here. So you can see from this diagram here that a grouting operation is quite simple. None of these machines or plants are very large. You don't need a lot of overhead clearance space, such as large cranes. So it's quite mobile and versatile to carry out grouting works. Of course, what you don't see here is what you see at the bottom here, the grout hole, right? If you want to carry out grouting, you need a hole, right? I say borehole, drill hole. You need some sort of hole to inject your pipes into. So one expensive component is perhaps these drill holes and boreholes. But they don't have to be vertical, they can be subvertical as well. If you do compensating grouting, they can be horizontal as well. But you need very tactical installation of drill holes before you can grout in the ground. So that's perhaps one of the challenges of grouting. So I mentioned a TAM pipe. So for those of you that have worked in the construction industry in summer months or for an internship, you probably heard this term, tube, manchette, TAM pipe. So this is not a type of grouting. Contrary to popular belief, this is a mechanism used to help you control the elevation of where you inject the grout. If you look at this cross section here, what essentially happens is for a TAM pipe, actually if you look at the bottom, you see these black and green parts. The black part is just like a rubber membrane around the pipe. And these rubber membranes are installed at fixed elevations on these pipes. What you can do if you want to inject at a particular elevation is you can first use packers. What are packers? Well, packers are just inflatable components that will close off particular locations of the pipe. If you look at this diagram here, there are two packers. There's a bottom packer and a top packer. So normally you drop this hose into your TAM pipe and then you inflate your packers. And once you inflate your packers, the grout can only be released at this elevation because it can't go up and it can't go down because the packer is quite snug against the inside of your TAM pipe here. Now, what's special about the TAM pipe? Well, the TAM pipe at this location here has a rubber sleeve. So when you increase the pressure at this point, the rubber sleeve will expand and the grout will squeeze out from underneath the sleeve. Now, you might be thinking, where's the grout coming from? Well, on this double packer device, there's actually a tube in the middle that's concentric that has a hole here between the packers. So if we increase the pressure in this concentric tube, the grout will come out, expand the sleeve, and the grout you can see in this particular diagram is coming out on top and bottom of the sleeve. So if you look at this diagram at the bottom here, the grout will come out from the green sides because the rubber black sleeve will expand. Why do we do this? Well, if we don't have this kind of device, we can't focus the location of the grout installation. These TAM pipes are a very interesting invention. They can be even made of steel. You see plastic ones here. The steel ones can handle much higher pressures. The plastic ones perhaps less. And the TAM pipes help very strategic elevation grouting. So you don't have to worry about injecting grout at the wrong elevation. So we often use these TAM pipes for perhaps remedial grouting for grout curtains because we want to know the elevation that we're injecting the grout. Even if the grout goes in the wrong place, at least you know you're putting it in the right elevation to start with, right? You may not have control about the area, but at least we have full control over the elevation. So in essence, the TAM pipe is giving you control for permeation grouting, which we'll talk about, because this method really relies on prior knowledge of where the grout's being injected. So these TAM pipes can be useful because the sleeve, unless you break it, can be reused. You can always come back to a particular location and set the packer from the top and bottom, inject the grout out again. You can go up in the TAM pipe. If you look at this bottom diagram, the TAM pipe can have different sleeve locations. So you can keep on traversing this fuel packer to the height that you want. And some grouting applications, we can create bulbs at certain heights. So this is what this TAM pipe can be used for. And if you refer to this name in the field or you hear in the future, it's not a type of grouting, right? It's not like compensation grouting, jet grouting, permeation grouting. It's just a type of tube used to help us control the elevation of grout injection. So in the next class, we'll talk about the different types of grout injection. But we can stop here at the TAM pipe today. So I'll see you next week.